Senator mentioned, I'm Dan Bartz. I own a little consulting business called Automation. We consult mostly in automated vehicle technologies and standards. Do a lot of work with the U.S. government. Today I'm going to talk about some of the architecture work I've been doing for the Society of Automotive Engineers. I am the Vice Chair of the Society of Automotive Engineers On-Road Automated Vehicle Committee, and I'm the Co-Chair of the On-Road Automated Vehicle Reference Architecture. And I'll talk a bit about what that actually means in a bit. So some of the things I'm going to cover, some of the takeaways are talk a little bit about the safety standards and some of the limitations of verification and validation, the V&V, some key definitions, a little bit about fault-tolerant design techniques, some lessons we can learn from humans. Believe it or not, you can learn things from them, and a bit about what we're doing at SAE. First, I'll start out with the DARPA Grand Challenge. Everyone seems to start there. This was one of the two vehicles I worked on. And one of the things that it was really unfortunate we didn't win. We came in second and third behind Stanford. But one thing it was invaluable in terms of learning was the value of fault tolerance. We had a pretty catastrophic failure. This was the vehicle everyone had expected to win. It came in third behind our slower vehicle. And it was because of an engine problem which cascaded to power and a bunch of other systems. We lost the primary sensor, this big dome up here, very early in the competition. But the vehicle had enough remaining sensors to keep on driving through the competition, albeit at a slower speed. And that was kind of an important lesson that I learned that I took home. Fast forward, this project I'm going to talk about started as a project for the United States Army TARDEC. TARDEC is the research labs in Michigan that does all the ground vehicle systems, including the automated ground vehicles. And this program is something called AMAS, Autonomous Mobility Applique System. And it was a program to take the existing trucks that the Army has and to give them various levels of both active safety for manned vehicles and higher levels of automation all the way up to a level 5 automation. In this video, we have one truck that's fully automated, and then these trucks have very limited automation, but they're able to take signals from the first truck. So that's a bit about where this. As part of this truck automation program, we started coming up with interface standards and a common architecture. And about a year and a half ago, we decided to take it from being a government contractor program to making it open to the industry and seeing where it went from there. We went to SAE, which is something the Army has done in the past, and said we want to make this open source. We want the industry to share it with the industry and kind of come up with some common. See where we can go with it. So I'm going to talk a bit about the safety, a little bit about safety. Over the last almost 100 years, 90 years, we've had a pretty significant drop in the fatalities per mile. In fact, we had fewer total fatalities than we did in 1950, even though we drive a whole lot more miles than we did in 1950 at this point. And where that gets us to is right now we're at 100 million miles between fatality. So if you're trying to design an automated vehicle system that's going to vastly exceed that's going to save lives, you have to be able to beat that number by a pretty large order. And keep in mind that 100 million miles includes the drunk driver and the drowsy driver and a number of people who are just not very responsible. And if you want to sell automated vehicles to people who are responsible, you need to make it safer than they would be, not just safer than the bad drivers. And so, I'm going to talk about some numbers about reliability, where what is considered to be acceptably safe. But just starting with, we're already at really big numbers once you start looking at how good humans are in the driving situation. Another thing I'm going to mention, historically to the Army, this was robots. This PackBot here weighs 50 pounds, goes 6 miles an hour, and has 76 joules of kinetic energy when it's moving. This head over here weighs more than a 757 airliner is at max takeoff weight, which is over 113 tons and more than 250,000 pounds, and is got almost 1 million times more energy than the PackBot does. 10 times more energy than a Hellfire missile does, kinetic energy than a Hellfire missile does. So, now we're dealing with the Army with some really big vehicles that have a lot of potential to do damage if they go out of control just from the vehicle itself. So maintaining control for automated vehicles of all sizes is important, but particularly when you get to car-sized vehicles, commercial trucks, and in this case, the even bigger trucks, the loss of control of the vehicle can cause catastrophic failure. And catastrophic failure for this talk is going to refer to a loss of life. Any event that occurs resulting in a loss of life is considered a catastrophic loss. The functional safety standards, which are standards that about how you design a system in a way that you can have pretty high confidence that it's going to be safe over a long period of time. And these were originally designed for the space program back in the 1960s by the Department of Defense. MIL Standard 82 was the first functional safety standard. Since then, it's been adopted across numbers of different industries. The aircraft industry has standards like DO 178. The rail industry uses variants of IEC 61508. And the last one on the right is the newest of the safety standards, ISO 26262. Now, up to this point, you're just hearing a bunch of numbers, and what does this really mean? So I picked the military standard just because it's the easiest to understand. Some of the other ones are a little bit more complicated. But basically what it says is when you design your system and you go through your analysis, you know how you figure out how quickly your parts fail, and you try to get it to a point where you've got what's considered an acceptable risk. So right here, if you're trying to get to a system that's considered a medium risk, and that means something in terms of the how much risk someone takes on when they use your system, it means that the likelihood that someone dies because your system makes a mistake doesn't happen more than once in every million system lifetimes. So if you've got a truck, average passenger car lasts 3,000 hours of driving. So that's 300, let me do the math. That's 3 billion hours if you just take that number and you multiply it by the million. Military trucks tend to last towards 10,000 hours. So that's 10 billion hours between catastrophic failure if you take the MIL standard at face value. So that's a really seriously high number in terms of catastrophic failure. But then you get into the other categories. If you injure someone or if you cause damage. So what this all means to the software engineer and the developer is that you have to design your system in a way to really make sure failures don't happen. And an insanely low amount of failures. This is what the auto industry started using. And to make their lives a little easier, they came up with this idea that if a human, these C numbers, it refers to controllability. If a human can take over, then allow you to lower your risk. So whether or not the human can easily take over, or it's a little bit harder for him to take over, determines which of these risk categories you put your system in. And what these things mean, what these ASILs mean, is how rigorous you have to be with documenting your software and going through your checks and making sure that your software is absolutely robust and provable and traceable, that you can show why you made every decision. And the higher the level, the more overhead it is, the more work. Well, the problem is nowhere on this chart does it say you can have a vehicle that doesn't have a human. And that's one of the things that the automotive standard wasn't designed around the idea of not having a human operator. So there's questions in the industry: do we need even higher levels of not letting the human involved, a level where we don't have humans at all? And do we need to have even higher levels of safety? And even to get to this point, the D means that your system doesn't have a catastrophic failure more than once in every 100 million hours. So these are really big numbers. And that's one of the reasons why my talk had the billion-hour problem, is that these types of systems need to be incredibly safe to be considered to consider the risk factor to be acceptably low. Now, this is pretty standard for people who've worked in kind of automotive industry, but this is the systems engineering V. It's basically one of the core elements in all of these standards and how you get to ensuring that your system is safe. And what we do in our architecture only kind of goes down to this level, but it's really important that that when you design your system, you have the ability to go back. When you run your tests and you do your verification, you have to be able to go back to your original design and make sure that every requirement that you started with is met every line has to come from a requirement. There can't be any dead code. There's all these rules in both software and hardware design that helps get that high level of certainty. Talk a little bit more about the Department of Defense, and then we'll get on some other interesting topics. But probably no one else in the world has spent as much money and time on these automation systems, the highly automated systems, as the U.S. Department of Defense. Literally tens, if not hundreds of billions of dollars. This on the left was the UCAV. It's a fighter jet without a pilot, and it's not a remotely operated aircraft like all the current aircraft are. It was designed to be fully autonomous. And this is the APD. This was a, I believe in this form it was a reconnaissance vehicle, but much larger than your car. This could drive over your car. In fact, I think they did drive over some cars just to show what it could do. It's a pretty monstrous vehicle. These programs were started because Congress said that the Department of Defense has to have 1/3 of their vehicles autonomous by 2010 for the Air Force and 2015 for the Army. And needless to say, they didn't meet those goals. And when you go into the conferences with these guys, and this is all public knowledge, these are open conferences, and you say, well, why can't you deliver these autonomous systems? You know, what's so hard? You have all these huge budgets. And the answer you get from everyone is, we can design systems with high levels of autonomy. We don't know how to verify and validate them. And, you know, all of these systems, they've been able to prove these extremely high levels of reliability. When you get to autonomous systems, now the tools don't work anymore. And this has to do with the fact that with autonomy, there's so many more variables and so much more state space, how many possible configurations the software can get in and the variables in the software can get in. You're dealing with systems that are adaptive and systems that are learning. Well, adaptive and learning systems aren't deterministic. They're not predictable. If we can't predict them, we can't take how they handle in the research lab or how they handle in the test ground and be able to say this is how they're going to perform, 5-10 years from now in the field. We can't take the lessons we learned from testing and say they're going to be this reliable in real life. And the other aspect is a lot of these systems are using some really great new computer architecture. They talked a lot about in these conferences about the potential of GPUs and some of these integrated system on chips. But the problem is a lot of these silicon is not deterministic, or we don't have models for it to know how it's going to behave over very long periods of time when you have millions of them. And I'll take a step back real quick. When I talk about 100 million hours between catastrophic failure, or 1 billion hours between catastrophic failure, that means if I build 1 million cars, I put them on the road, 1 million autonomous cars, and I put them on the road, in the first 1,000 hours of driving, there might be one fatality. That's what 1 billion hours between catastrophic failure is. So 1 million vehicles, one has a failure over the 1,000-hour window that could lead to a fatality, and that's a pretty high number. So part of our SAE group and part of what we did with this architecture activity was we went out to industry, tried to get some of the best experts we could, both government folks in Department of Transportation, automotive suppliers, automotive manufacturers, universities, DoD contractors, consultants like myself, and try to put our brains together to really figure out how we can get to the next step with some of this technology. So I'm going to show you the end, or what we came up with first, and then I'll explain how we got there. This is kind of a high-level view of the SAE functional architecture. I've kind of cleaned up all the little details just because it's kind of busy if I didn't. But it's basically 4 layers of control, each running at a roughly an order of magnitude time scale apart, and different levels of criticality. This top level is mission critical. If this fails, if anything in this system fails, and failure means it can no longer operate the way it needs to, you might not get to where you're going, but nobody gets hurt. Safety critical, which is these 2 bottom layers, means they have to keep on working even when they have a fault or a failure. They're called fail operational. And those are the things in this architecture that we need to really safeguard and ensure get to those high levels of reliability. The stuff up here, we want to get high enough reliability that we don't annoy the customer, or that we make a product that we can feel proud about. But we think that we need to focus on the safety aspects of the system. I'll explain how we get here in a bit. So I'll talk a little about real time. There's 3 different types of real time. One is called hard real time. What real time means is you have a job that needs to get done, and you have a deadline by which you need it to get done by. Hard real time means if you don't meet the deadline, people can get hurt, people can die. You must meet your deadlines. Hard real time systems are guaranteed to meet their deadlines by design. If you got code you have to run, you go through every possible execution branch and make sure that you never exceed that time window. A software time system, maybe something like Netflix, where if you miss your window, it's okay. The information still has value, but you maybe you're watching Netflix and it has to buffer for a second. You're a little annoyed, but there's not much worse for the wear because you had some broken deadlines. And then the middle class is something called firm real time, and that would be kind of like a phone call where there's no value in processing old data, so you really want to try to get it there when it needs to get there, but there's no negative consequences of meeting the deadline. So this type, the hard real time, is mostly what we're going to focus on in this talk. And like I said, keep in mind that these things have to meet their timing execution. And 2 other terms, I know this might be a little dense. Determinism and non-determinism, or deterministic and non-deterministic. By the way, Andre asked me to put gold stars wherever a real important concept is, and I decided to put a gold Death Star, because I think it's a better type of star. But anyway, a deterministic system is one that's guaranteed will complete its process by its deadline, and that for each combination of inputs, you get a unique set of outputs. You have a predictable set of outputs, and so that you put in some values, you know what you're going to get out. This helps, like I said, when we get into both the testing and also the analysis of the system. When we talk about non-deterministic systems, these are ones that either don't meet their deadlines under some circumstances, or when your computer has to do some caching. If it slows down your process, you don't meet your deadlines, you're no longer it can ever happen in your system. It means you don't meet that hard real time requirement. If your system has different states with the same inputs because you're using random values, or you're using a hardware timer for something, or some other data that isn't coming through inputs, that would make your process non-deterministic. And also, if your system is designed in such a way that a piece of hardware failing makes it not work the same way, that it's not deterministic. We're designing systems so that even when hardware fails, the system works in a predictable way. So, this is just going to talk about some of the things we're going to look at. Looking at time, so I'll make sure I get through all the rest of it. But when we designed our architecture, these are the types of things that we considered. I won't bore you with this slide. Talk a little bit about cybersecurity. In December 2011, the Iranians claimed they captured an American RQ-170 drone. They claimed they did so by using a very sophisticated Russian GPS spoofing system. For a while, the U.S. denied that they had it until the Iranians showed video of it, and then, okay, they had it. We asked the researchers to go out and try to figure out if they could reproduce what the Iranians did. And a few months later, a team at University of Texas, Austin, was able to take control of both a small drone and then eventually an $80 million yacht by pretending to be the GPS satellite system with several $1,000s in hardware. Just last year, a group of Chinese hackers open-sourced a GPS spoofing software package, and now you can do it for $300. And I just want to keep in mind that not only can you spoof GPS position, but you can spoof time. And there are a lot of robotic systems that are safety critical that I've seen that use GPS time for really important things. And just keep this in mind. Someone can really mess with your system very easily, and there is no traceability. So when we start thinking about these types of external vulnerabilities, we need to consider that in our design. And I'm going to give you some examples, and these examples are some examples of what hackers could do with automated vehicles or connected vehicles, but they have faults that occur naturally that are almost the same thing. And as we design our system to be tolerant to faults, we also want to make sure that we're tolerant to the same types of, or we'll be able to make our systems tolerant to a number of different cyber attacks. And so some in the safety community look at cyber attacks as malicious faults. Now, here's a circumstance where a GPS spoofing system tells a vehicle that it's in a position other than it is. It tells the vehicle behind it that it's right on its bumper, and the second vehicle's warning system goes off, or maybe even worse, it applies the brakes. This is what we would call what's called a Byzantine fault. It's because we don't know who is the guy who screwed up. Was it the car in front of us, or was it this, off-board guy, or the positioning system that told him where he was? And the way the standards are set up for DSRC, you have to use GPS. So, this raises a lot of questions. But we have the possibility of either doing sensor spoofing or sensor jamming. There was some recent articles about someone who claimed to have spoofed the LiDAR. My understanding is pretty hard. Jamming a LiDAR is actually a lot easier. All you have to do is put out a signal in the right wavelength with enough background noise that you swamp the target and the receiver no longer gets discernible returns. The DoD does this a lot when we're testing new vehicle systems. Whenever we're testing a robot with new sensors, they're expected to be able to at least detect the situation. But this is the same thing that would happen if your sensor failed. And so you've got to design your system to be robust to these types of things. And we're going to talk about the networks inside the vehicle. So we heard about the hackers who were able to crack into Jeep Grand Cherokee remotely, one that had never touched before, get on the radio, and go and tell all the other devices, tell the steering column that it needs to go to this angle, and tell the brakes it needs to go to this position, by pretending to be other modules in the vehicle. So they were sending out messages with fake origin addresses, you can think of it that way, that the other modules didn't know the difference. Okay, well, one thing automakers are saying, well, let's put authentication on everything so we can detect those fake messages and we won't listen to them. Well, when you start talking about an autonomous vehicle or a safety critical system, not getting messages means your vehicle is now potentially in a catastrophic failure, or you have a safety critical element when your vehicle is traveling at speed. And so the bad guy doesn't have to spoof anything. He just floods your bus with random messages in a denial of service attack. But this is also a failure that happens naturally for people who have ever used these hardwares. The babbling idiot is the denial of service attack that occurs because a hardware fails in a very particular way. So even if we're not just thinking about hackers, we've got to be thinking about the ways in which the hardware can fail. And taking down the network is a pretty sure way that we're not going to be able to guarantee our safety of our vehicle system. Now, hardware failure, we know if hardware fails. We know with a number of different processors how much they fail. They also fail in ways where they don't stop sending messages. They may send bad messages or screw up a calculation because a radiation particle flipped a bit in a register, and now the processor is putting out bad data. So one way, or two ways that these are accommodated for, is either taking the output of 3 different computers and then comparing them through a voter, and whichever majority wins. Another one is what's called a fail-silent approach, where you have a main computer and a smaller checking computer that checks your main computer to see if its calculations agree. This is how your throttle pedal works. If you remember the whole Toyota thing, there's an engine controller, and then there's a small separate processor that just has an algorithm that says, is the output the engine controller asking for consistent with the pedal position the customer is asking for? If it's not, I shut down the engine controller. If you have 2 of those, now you can get to a system where a single point failure in one of your processors shouldn't take down your ability to compute. And so this is a really, and one other thing, Boeing likes to use multiple different architectures of processors, different brands of processors as their redundant processors, on the off chance that there is a hardware bug that hasn't been discovered yet. And the thought being is that Intel and AMD and Motorola won't all make the same hardware mistakes, but sometimes those actually do happen. But some people really go out of their way to make sure that single point failures don't take down their system. This is a Nissan steer-by-wire system. It still has a mechanical steering column with a backup clutch in case everything fails, but they're designing the system to be robust enough that it can survive failure by having 3 computers, as we talked about triple modular redundancy, 2 steering motors. In case one fails, the other one is still available. There are 3 sensors in the steering wheel to measure the position, and then the network it has connecting everything together is a FlexRay network, which is a network designed around safety critical performance. It's designed to be resistant to faults. This is another example of a program. This is a truck program in Japan, truck platooning or truck tuning program. This is one of their coordinated stops. Now notice the trucks maintain a 4-meter gap all the way to stop, within 10 centimeters of air. This is a program developed by the Japanese government. They had some really heavy reliability requirements that they were trying to meet, and they thought were appropriate for this type of automation. Each vehicle still has a human in it. It still meets that criteria of humans can take over if there's a failure. But even here, they're designing for a failure rate of no more than once in every 100 million hours. And even the lane sensing system should never get less than once in 1 million hours having a lane detection failure. And the network between the vehicles, the wireless communication, needs to be 99.92% reliable. So these are all really high numbers that a lot of the automated systems, none of the automated truck programs had met before. This is part of the way they tried to achieve it. They have a forward-looking LiDAR and a forward-looking radar looking at the same thing. And they're different types of sensors because all sensors have failure modes. The environment can cause situations where the LiDAR is jammed because of fog or dust. Radar can get interference from metal on the surface of the road or on the side of the road. But having 2 different sensors with 2 different failure modes makes it a whole lot less likely that they're both going to be taken out. The trucks have a wireless communication system called DSRC. It's very similar to Wi-Fi, but designed for vehicles. The U.S. is also looking at DSRC. But in addition to DSRC, they have a wireless infrared communication system just in case they lose some messages from DSRC. You can see on the right they have 2 different lane following systems, one based on LiDAR, one based on camera. This is what they thought they needed to do to get to those levels of reliability. And then on the inside, I don't have a picture of it, but the computer that ties everything together is a multiple redundant computer out of a Shinkansen bullet train, which, by the way, is probably the only transportation service in 50 years has never had a fatality caused by operation. And so they've been really good at having redundancy on all their computer-controlled systems on that train. This uses that same type of redundant computing controller. Now here's a example of a rocket. Notice the little Death Star up in the sky. This is the Ariane 5 rocket. I believe it was 1996 when this launch happened. First launch. Beautiful new rocket. Pride of the French space industry. It was taking the place of the Ariane 4 with a $500 million satellite on board. Fully redundant system. They had all this checked code. And a lot of it had been reused from the Ariane 4, and so it took them a while to figure out why that happened. After, I forget if it was like a year or more, someone, a PhD student developed this new software process that was able to find the one bug in the line of code. It had been a section of code that had been from the old rocket, the Ariane 4, that had worked great in the Ariane 4, never had a problem. And all of the safety checks of the Ariane 4. The Ariane 5 didn't actually use the value that came out of this code, but it executed it. It was dead code. And what happened was when the computer executed this, it had a buffer overflow because it was trying to put a bigger value than 64-bit double into a 16-bit int. And that worked on the Ariane 4 because the Ariane 4 couldn't go fast enough to exceed the 16-bit integer. But when the Ariane 5, a faster, bigger rocket, did, it caused a buffer, integer overflow. There was nothing to handle it. There was no handler written because it couldn't have happened on the Ariane 4. And the entire processor crashed. Switch over to the backup processor, runs the same line of code with the same variable values, and it crashes. The rocket no longer has directional control. And the important lesson to learn here, several, is we want to be very careful about reusing code. You can't just use code and say it worked great on this other program, it's going to work here, because the original program had very specific assumptions. The other thing that's very important is that hardware redundancy doesn't solve software design bugs. You can have reliable hardware, and you don't get, if you don't design your software robustly, you'll get things, unfortunate things that happen. Getting a little close on time, but I'm going to go through these pretty quick. What's your call? One of the things that has been done because of this situation of having the two pieces of code run the same bug is the idea of using different software in your flight controllers. And in this example, we have a high assurance flight controller, one that is really robust, it's simple, it's been proven with all the techniques that we have, but it's only provable because they've kept it simple and it doesn't do all the bells and whistles. Then you have a high performance flight controller, which has all the bells and whistles. It's the fuel efficient flight controller, it's really smooth, and it does all these high performance things. But in the case that it fails, you can switch over to the high reliability, high assurance flight controller. So this is one example of a pattern called simplex. This is a different version. One thing I want to point out here is that these things called acceptance tests. Those are like those checkers I mentioned earlier that it's much easier to run a small piece of code to check that the output of a bigger piece of code actually was successful. And you do that independently. So let's look at how this is done in the human. The human actually has two pathways for perception. One we call the dorsal, one we call the ventral. The dorsal pathway is the one that deals with motion, deals with collision avoidance. It's very fast, very robust, very deterministic, but you're not consciously aware of it. It's kind of in the background. And when you're walking around a room and, you're about to run into something, you don't even know that you're about to run into it because this gets you out of the way. The ventral system is where we look at our intelligence and our ability to perceive and understand the world around us. But the system is slow and it's undeterministic, but it's incredibly powerful. Combined, these two work to keep you alive. And I'm going to show you a little video. In fact, I'm going to skip a bit of it. Nope. I'll just do this back.
Well, blind sight is this term introduced by Larry Weisskranz to describe the ability of people like Graham to detect things, but not to be aware of them.
So someone who's lost the perception, the high-level awareness,
vision,
but still maintains that low-level unconscious awareness. It's called blind sight.
Thing that this phenomenon of blind sight teaches us, it is that vision is not entirely seeing, that there can be a disconnection from the capacity to respond to visual information and the actual act of being visually aware of something. Those two things can be separated and probably are in our everyday lives. But the problem is that obviously we're not aware of the things that we're not aware of.
Well, if you look at the anatomy, you can begin to explain this curious syndrome. It turns out from the eyeball to the higher centers in the brain where you interpret the visual image, there's not just one pathway, there are two separate pathways which subserve different aspects of vision. One of these pathways is the evolutionarily new pathway, the more sophisticated pathway if you like, that goes from the eyeball through the thalamus to the visual cortex of the brain. Now you need the visual cortex for consciously seeing something. The other pathway, which is older evolutionarily, goes to the brain stem, the stalk on which the brain sits. And from the brain stem gets relayed eventually to the higher centers of the brain. Specifically, the older pathway going through the brainstem is concerned with reflexive behavior, orienting to something important in the visual field, making eye movements, directing your gaze, directing your head towards something important. In these patients, one of these pathways alone is damaged, the visual cortex is damaged. And because that's gone, the patient doesn't see anything consciously. But the other pathway is still intact. In a sense, we experience blind sight all the time in our daily lives. For example, as I am driving this car and having this conversation, all my attention is on the conversation, on the person next to me. And in fact, I'm not conscious of what's going on around me. Even though I'm negotiating all this traffic, avoiding obstacles, avoiding that car on my right, avoiding the car on my left. That's all being done in parallel by another part of my brain, and it never emerges into conscious awareness unless something very strange happens, like a big truck passes by, I might notice it.
So by learning about blind sight in the patients who have it, we're able to learn a lot more about how the brain operates, and also about how we drive it. I like this documentary. This is, by the way, I think Secrets of the Mind on PBS Nova. That concept became really important to the architecture. I'm going to finish up. I've got 3 more slides. One other thing humans do to deal with complexity, we look at how we manage our day. We think about the minutes of the day, but then we think about days of the week. We don't plan minutes of the week or minutes of the year. We have higher abstractions when we look out further into the future, and that's how we plan. This keeps our life manageable and simple. One of the architectural concepts we borrowed from NIST was breaking down the task that the robot has to plan into the same types of time hierarchies. Every layer being 10 times slower, but looking at 10 times farther. And by breaking down all of the planning you have to do along this way, any one layer can be analyzed with only 20 steps. It reduces the amount of states in the system and makes it easier to analyze. And there's a whole bunch of papers, and I'm kind of running out of time, so I don't get into the details, but this is a really important concept as well. The last one in terms of the lessons we learned is the networks are really important, fault-tolerant networking. I can give a presentation of fault-tolerant networking. I have. You need redundancy. You need to make sure that your network guarantees you get your messages there on time. You need to make sure your network prevents rogue computers from taking up the network. And often with these data buses, clock synchronization is done by the network itself. In fact, how you get these other things is often a function of the clock synchronization. But the next talk, Stan will talk a bit about some of the stuff they're working in a similar area to this. So putting it all together, we have our lower safety layer. We have conventional automotive controls, ABS, stability control. We have what looks like your active safety systems, but it's also that lower level perception, the faster, simpler perception. The world is made up of objects. Doesn't catch everything, but it works reliably and it's predictable. We can validate the system mathematically. We can prove the system will behave the same way years and years and years. And on top of that, we add a higher level perception. We're talking about deep learning or these AI algorithms, advanced planners. That happens up here. Your advanced fusion, your advanced maps, your advanced planning systems happens at this higher level. It's slower because it needs to absorb more information. It needs to process more things. And it's also looking at further out. What we call the mission layer here, that's beyond what your sensors can see. The local layer is the extent to which your long-range sensors can see, and you're planning ahead. The safety layer on this diagram refers to the things that happen really quickly and have to be responded to very fast. And then the control layer is even faster. It's the reflex action when your car hits ice or loses control. When you put these all together, this is what we have with the SAE reference architecture. And each one of these things we have gone into much detail defining them. But all of the pieces we just talked about in terms of redundancy and the different ways of breaking down perception and the time hierarchies are all things that we felt were really important to design an architectural framework that it meets these fault tolerance criteria. And as an SAE group, it's an open activity. Anyone who wants to participate, anyone who wants to work with us on this, it's like I said, it's open to everyone and anyone. We've got a number of automakers and auto suppliers involved, and my call to action up. And I think that the little paper tab will have has my contact information on it if anyone gets involved. But there's my talk. Apology, I'm a little over, but hope not too much. But
all right, folks. Let's put our hands together for God.